In this last section of 20, we're going to finish up with optimization using trig functions. So this is just a specific example of one that uses trig situations based on the story problem. And again, all of the optimization problems are going to look very similar. It's just going to be what kind of derivatives you're going to be looking at. So in this one, we're looking at needing derivatives with sine, cosine, or tangent. So to begin with, understanding the problem, we have two corridors that meet at a right angle and are 2 meters and 3 meters wide respectively. Angle theta is the angle marked on the given figure AB. Is a thin metal tube which must be kept horizontal and cannot be bent as it moves around the corner from one corridor to the other. So in the end, what we're looking at is what does, in essence, the length of AB have to be. So it says show that the length of AB is given by the following. So based on what I know, I'm going to label this part here X and this part here Y. So that's just based on each of those two segments. And then what I do know also, I have a triangle here. There's a right triangle there, and then there's a right triangle here. This triangle has a height of 2. This triangle has a horizontal length of 3, but they're specifically right triangles. The other thing that I know is because this is a horizontal line, as is this, if this angle is theta, that means this angle here also has to be theta. I'm going to clean up my picture here. So for part A, they want us to show that the length of AB is given by that statement. So what I do know right now is that my AB, that segment AB, is made up of X plus Y. And that's still L, as I said before. So I need to figure out what is X, what is Y. So based on the fact that I have a right triangle, this side is adjacent. This is hypotenuse from this angle, so therefore the cosine of theta equals 3 over X. And then for Y, this is my opposite side, this is my hypotenuse, so opposite and hypotenuse uses sine. So therefore the sine of theta equals 2 over Y. So now I just solve both for X and Y, and I can substitute them back into this equation. So therefore X equals 3 over the cosine of theta, and Y equals 2 over the sine of theta. So therefore my length equals 3 over cosine theta plus 2 over sine theta. So that's the first statement that they wanted us to show. Okay, so moving on, now they want us to show that the derivative of the length with respect to theta is 0 when theta is etc. So this is a very typical problem that you're going to see. So they want you to figure out the second part. So they want all of your work to show the theta equaling tangent inverse. So that means you have to start with the first part. So you have to start with your derivative set equal to 0. Well, in order to even do that, you need to be able to do your derivative. So therefore, let's do dl d theta. So keep in mind that the above statement is exactly the same thing as 3 cosine to the negative first of theta, so if I move them up to the top, plus 2 sine to the negative first of theta. So now when I do my derivative, so I have to bring down the negative 1, so that becomes a negative 4 times the cosine to the negative second of theta. I don't know why I made that a negative 4, that should be a negative 3. Sorry about that. The negative 3 times the cosine to the negative second of theta, and then the derivative of the cosine of theta we learned in the last section, so times the opposite of the sine of theta, or negative sine of theta, either way you want to think about it. Plus, so now I'm going to do the derivative of this, which is negative 2 times the sine to the negative second of theta, times the derivative of sine of theta is cosine theta. Don't forget to take the derivative of that function still. So we can rewrite this just slightly. This is L with respect to theta. This is equivalent to the negative 3 and the negative sine of theta. That's a positive 3 sine theta. I'm going to drop the cosine squared down below. That way it has a positive exponent. And then minus 2 cosine theta over sine squared theta. Okay, so I'm nowhere near done. I just found what my derivative is. But now, since I want my derivative to equal 0, I'm going to have to combine this as one single fraction. Because I know at least if I have a fraction, and I have that fraction equal to 0, what has to be 0? The numerator is 0 for the function to be 0. So therefore, once I combine them together and I have a single fraction, then I can just set that numerator equal to 0. So I've got to get common denominators. So this left fraction is missing a sine squared theta on the top and bottom. So I already have a sine of theta on the top here, so sine of theta times a sine squared theta is the sine cubed of theta. And then this bottom needs, or the right fraction, needs the cosine squared of theta, but then the top also needs the cosine squared of theta. Since there's already a cosine of theta there, that means there's 3 of them. So now I have common denominators. So dl d theta equals 3 sine cubed theta minus 2 cosine cubed theta all over the common denominator, cosine squared theta, sine squared theta. Okay, now that I have it as one fraction, I'm going to set that numerator equal to 0. So therefore, 0, oops, I don't know what happened there. Try that again. 0 equals 3 sine cubed theta minus 2 cosine cubed theta. So if I move the 1 over to the other side, so I'll move the negative 1 over, so 2 cosine cubed theta equals 3 sine cubed theta. What I'm trying to do is I'm trying to get theta by itself. Okay, that's really what my goal is. So right now I'm just trying to reorder things so that I can get my thetas on one side and my non-thetas on the other. So I can divide both sides by 3. And then I can also divide both sides by cosine cubed of theta. Now you might not realize why I'm doing this, but I know something about a relationship of sine over cosine. So therefore, if 2/3 equals sine cubed of theta over cosine cubed of theta. And let the top help you. It's telling you what it should be. It's saying tangent inverse. And you know tangent is the sine of theta over the cosine of theta, which is what we have here. And instead of sine of theta over the cosine of theta, I sine cubed of theta over the cosine cubed of theta, which is equivalent to tangent cubed of theta equals 2/3. So if I want just the tangent of theta, or excuse me, if I just want theta, what I have to do is I have to get rid of the tangent and the cubed. So the first thing I'm going to do is get rid of the cubed. So I'm going to cube root both sides. Cubed root of 2/3 equals the tangent of theta. Get rid of that exponent first. Now I can get rid of the tangent with the inverse tangent. Tangent inverse of the cubed root of 2/3 equals theta. And that is what they wanted us to show. And then we could type that into our calculator if we really wanted to, and we would get that decimal approximation. And there we go. So we showed it. Perfect. Okay. And then the last part, part C, said find L, so find the length when the tangent inverse of that, when theta is the tangent inverse of that, and then comment on the significance of it. So since we know that theta, therefore, is approximately equal to 41.1 degrees. Now, if you're doing this problem on the actual test, make sure that you store That value should have the exact value until the very, very end. If they just wanted to know what theta was, that's your answer, 41.4 degrees. So now you've got to take that value and plug it back in because they want to find the length. So that's what part C is asking for. So for the length, is 3 divided by the cosine of 41.4 degrees plus 2 over the sine of 41.4 degrees. And when you type that into your calculator, you get 7.023, and that would be meters. So the significance of that means it has to be 7.023 or less in order to make it around the corner because it can't bend. Okay, so that's what we're looking at there, is finding out where that zero value was so that we could find like the maximum or minimum that we could have. So that goes with our optimization problems, making sure that you can now just apply it to all of the different derivatives we now know how to do. So now you should know how to do all the derivatives that you will be accountable for, and you should be able to do real-world applications with them in addition to just finding basic derivatives.